seminar series. So today we have Brian, and he's gonna talk about the quantum imaging. So a little bit about Brian. He's a quantum algorithm designer with deep roots in computer science and data science. He had been exploring the general artificial intelligence, including NLP, processing, and machine learning, when he accidentally discovered the cloud-based quantum computing. His most recent projects have been combined elements of all areas, emphasizing quantum machine learning and culminating in Quantum MNIST, a direct challenge to Google's TensorFlow Quantum. He recently published a unique quantum computing book called Dungeons and Qubits, which represents quantum algorithm design and style of Dungeons and Dragons adventure. I had a great pleasure reading that. It was such a good book, very light tone to it. I also want to mention that Brian has military experience. So today we have large number of audience from the D&D and Canadian Armed Forces. So, so yeah, Brian, it's over to you to entertain them.
Oh, thank you very much. Let me start by saying that it is an honor to be invited to speak with you. I will talk about what I have done with quantum imaging. Then I will talk about things that I have not actually done myself, but we can do now, at least a dog and pony show. And then I'll go into a little bit of things that we can't actually do now, not in any even remotely practical sense, but are exciting things that will be possible in the near future. I don't know everyone's background, so I will go in a sine wave. I'll go a little high level, less technical. I'll dip down into a little more technical, and I'll just ride the wave there. And I'll also try to be not funny. So if you laugh at any point, I do apologize. The single largest imaging project that I've worked on through completion is Quantum MNIST. And MNIST, if you're not familiar, is a data set of handwritten digits, the numbers 0 through 9. And if you get into machine learning, it's largely unavoidable, because what happens is you're building a model, you're training a model, you're testing a model. And in the real world, you always worry about your data. There's always something wrong with your data. But the MNIST data set is so thoroughly tested that you really don't have to worry about the data. You can focus on your model. But as a consequence of that, if you look through GitHub, Stack Exchange, and other places, you can find the source code. I characterize it as a problem that is not in need of a solution. Everyone's done it. It's kind of boring. And to be completely honest with you, I skipped over it. And I looked on to, I moved on to something more challenging until I was working on quantum classification. And originally I was working with data that I was just making up on my own in order to test that the algorithm was working, until he contacted me, a postdoctoral research fellow who had real world data, and he wanted to do quantum classification with it. And it was still relatively small, just a couple of features. The number of records was in the 6 figures. I'd like to say 200,000 something. And it was my first time with a quantum algorithm working with something of that size. And of course, there was a data problem, and we troubleshot that and came up with something that actually worked. We looked at it, it was classifying properly. And when I shared it, I was being heckled by a couple of YouTubers, because we all know that the education system works. You've got PhD, postdoc, and then YouTube on top. And they were heckling all sorts of things. My algorithm will never achieve quantum computational advantage, even though there's plenty of research suggesting advantage for it. What was the other critique? They didn't like the encoding method, although that's in use by other people also. And I'll get into that, how I encoded it, in a little bit. And the size of the data set they criticized. They said it was very small, even though quantum computing really can't do much right now. I thought it was pretty good, but it was very small compared to MNIST, which one of them characterized as a toy problem. That was his exact quote. And classically speaking, you can't argue with it, but from a quantum standpoint, those are for quantum, it's a fairly large image. There's lots of images. So I thought that was a good step forward. Let me tackle MNIST. At that time, I only knew of one implementation of it, which was Google's TensorFlow Quantum. At this point, I only know of one other besides that at this point. But TensorFlow Quantum at the time, unless they've added to it, was very limited. You had a 16 pixel image. So it's just a 4x4 image, and it was binary, just black and white pixels only. And you could only classify the numbers 3 and 6. That's it. So very limited. And I decided, well, everybody does binary. If you look at quantum neural networks, if you look at quantum machine learning, everyone's doing binary because it's simple. So let me try grayscale. We have superposition. We can encode values between 0 and 1. And let me also try all 10 digits instead of just 2. And let me also set myself the additional challenge of not using Python. Everyone uses Python. So I decided to use Microsoft Excel for the pre-processing and the post-processing. And I just had one open chasm circuit. When you don't use Python, you can focus on the actual quantum circuit and what the quantum processor does. And you don't use classical computing as a crutch. You can do all these things. So I look at it the other way. How much can I do with a quantum processor or the simulator? And I'll only do classically what I absolutely cannot do quantumly. And as a disclaimer, I only tested the digit 0 because Microsoft Excel was so hard to work with to do all that. So I should have used Python. Python would have actually made it a whole lot easier, but it did work. Out of all 10 digits, the algorithm said that the test 0 was most likely a 0. And considering you're going from an image that's close to 800 pixels and you're compacting it down, you're compressing it down to only 16, you're losing a lot of information. But I would have been content if the result would have been a 3 or an 8, something with similar curved features at the top and the bottom, as opposed to, let's say, a 4 or a 7, which look nothing like a 0. But fortunately, the 0 came back as a 0. And the method is very simple. This is where I'll get a little bit technical. I call it the swap test. When I learned about it, that's what it was called, the swap test. It has many names: kernel methods, or inner products, distance measures, because one of the biggest challenges to getting into quantum computing and quantum mechanics is everything has to be unnecessarily confusing. Everything has multiple names, or it's named after people, which is great, except that it's very non-descriptive of what you're working with. The swap test, you have two quantum states: the canonical swap test or the textbook swap test. If it wasn't a textbook, it should be in a textbook. You have two quantum states, let's say 1 qubit each, and then you have an ancilla qubit, and that's your workhorse, this workhorse qubit, and you have two Hadamard gates, and sandwiched in between the Hadamards, you have a Fredkin gate, which is also called a controlled swap. The ancilla is always the control, and then the swapping qubits would be the ones that you are comparing. And if you have a multiple qubit state, you simply compare the appropriate qubits. So let's say there's a 2 qubit state, Q0, you have the control on the ancilla and put the controlled swap on Q0 and Q0, and Q1 and Q1 and just compare like qubits. Then you measure only the ancilla qubit. And when you read papers about this, they generally tell you that if the states are identical, you will measure zero 100% of the time. And if they are not identical, you'll measure zero 50% of the time. And that isn't the full picture. What'll really happen if you run the circuit a few thousand times and you look at the results, if two states are very close together, they'll measure zero closer to 100% of the time, maybe 90%, 95%. And if two quantum states are pretty far apart, they'll measure zero closer to the 50% mark, maybe 55% or 60%. So it won't just tell you if they're identical or not, it'll also tell you how similar or dissimilar they are, how near or far apart they are, which is why you can encode the digits 0 through 9 on qubits, and you can take a 0 and compare it. And the 0 was the highest percentage at 90 something. It was 90 something percent. And the worst was around 70%. And all the others were somewhere in between. And as far as quantum computational advantage, there was a paper that I read before the Google quantum supremacy experiment that using this method suggested that the magic number might be around 50. And that would actually be referring probably to quantum computational supremacy instead, but I'll get into that in a moment. 50 qubits, if you have two 50 qubit states and an ancilla qubit, so 101 total qubits. And at that point, the math, the computation might be more than the classical computation can handle. And you can kind of test that now, actually. We don't have that many qubits. We don't have any fault tolerant qubits. But if you take any simulator and just load up all the qubits, just load it up with gates, you can determine the breaking point of that simulator. For IBM, I've actually done that. It's somewhere after the 2-hour mark. If you load up a circuit enough, you'll get a runtime error on it. But more recently, the Google quantum supremacy experiment, which did not actually achieve supremacy, it got really close. It used 53 qubits, and I believe it was Dr. Scott Aronson who suggested that if Google just had 1 or 2 more qubits, it would have been indisputable that the Summit supercomputer would not be able to compete. But at 53 qubits, it was a difference of 200 seconds versus 2.5 days. Impressive, but not decisive. It's just a long weekend. You run it on Thursday, come back on Monday. But using that projection of 1 or 2 more qubits, which side tangent, the processor actually had, they just weren't functioning. I'll go with the number 55 if we compare a 55 qubit state to a 55 qubit state plus 1 ancilla qubit for 111 total qubits, that at that point, maybe a supercomputer can't keep up with that. But we can't actually test that now. I'm an experimentalist. I like to actually run it and know for sure. But based on this early paper and the 53 qubit experiment, I would like to offer my personal hope that around 111 qubits, we can test it and see how it actually performs. There are limitations to the experiment as I did it. I used mean digits. Of all the zeros in the data set, each pixel has an intensity between 0 and 255. And I had to compress that down. I didn't want to use 16 pixels because that's what Google did, but because of the limitations, I couldn't run it on real hardware. because of the limitations of the simulator, I had to compress it down. So each new pixel of mine contained 49 original pixels in a 7x7 grid. So 49 values ranging between 0 and 255, sum them up and then normalize them between 0 and 1, which is also a machine learning trick. If you don't normalize your data, sometimes you get really undesirable results. And then for quantum computing, you can just extend that. Instead of 0 to 1, it's 0 to pi, which is a half rotation around the qubit. Compress it all down, so I ended up with 16 values between 0 and 1, which became 0 to pi. I used dense angle encoding, so a rotation around the y-axis for one, then a rotation around the z-axis for the other. And that's not necessarily the best method. If you want to represent the zero, taking a mean zero, there's a lot of variation just in how people handwrite digits. That you could do standard deviation or binning, and both are approaches to say, well, here's a zero, and here's the variation in this direction and the variation in this direction. But it's hard to say that that would produce more accurate results. My concern would be that you'd probably just blur them together. And that was a concern of mine, taking near 800 pixels and compressing it into 16 and losing all that information, that maybe all the numbers might just blur together, which is why I was so happy that my experiment worked at all with all of that blurring taking place. So it's not necessarily the best approach. More testing would have to be done. And well, I'll get into a bit a better method that has actually been tried recently. Another limitation is that MNIST uses the whole image, and what's far more practical is that you'll have a feature that you want to find in a larger image. And at first I was thinking that would probably have to be a variational algorithm, which is classical code. And I'm not a fan of variational algorithms at all, because you have a lot of classical code. And it's like playing Where's Waldo? Where's the quantum circuit hiding amid all of this Python? And you would need classical pre-processing and classical post-processing, and you need mid-processing all throughout. But while I was thinking up what I was going to say today, it occurred to me that it's much simpler than that. You can just encode the feature in a couple of qubits, and then comparing, let's say, it's not useful to say 16, but let's say we've got a 16 pixel image, take a 4 pixel feature, and then make multiple copies of that, and then just compare it to the full image. The problem with that, well, the advantage to that would be if you have enough qubits, you have an original image, you make a bunch of feature encodings, and then you can do a lot of searching at the same time. The downside to that would be it's very classical thinking, and anything you do in quantum computing that sounds like classical thinking is probably not the best way to do something. But at least for now, that is one possible option, that you can just take the feature, and using the swap test also, let's pick a number like 95%, that these feature qubits match these qubits 95%. So let's take a look at that area of the image, and let's see if that's what we're looking for. And then another limitation is most images use two-dimensional pixels. I started working on a project at one point that would have used three-dimensional voxels. And you can imagine a brain scan. You take two-dimensional images, and you take multiple slices of the brain, and then you assemble that into a three-dimensional image of the brain. so that the feature you're looking for isn't two-dimensional anymore. It's three-dimensional, or it's facing, you don't know what position it's in necessarily. And for a small example of that, you can just keep track of it the way I did with MNIST, which if you're only using 8 qubits, then this qubit is the top left corner, and this qubit's the top right corner, and this qubit's the bottom left corner. It's easy to keep track. For anything much larger than that, there are proposed algorithms for other ways to keep track of the spatial information. What part of the brain am I looking at? The downside is that you need additional qubits for that. You're using qubits to encode the spatial position, and we just don't have those qubits right now, which means that if you wanted to test it experimentally, you would have to have a very, very small image. And then very recently, within the past few weeks, there was a paper by QCware. They used an ion Q system. And they also, among the things that they report doing is Quantum MNIST again, but they used amplitude encoding, which is something I had on my to-do list and never quite got around to it. And I'm going to very grossly oversimplify it. Imagine between my wrists is a binary string. We just have a bunch of bits between 0 and 1. The idea is the quantum Fourier transform works like a digital to analog converter, like I'm going to date myself by saying a modem, but we have this binary string and we're going to turn it into a wave. And you can see my wrists are now much closer together. And then the inverse quantum Fourier transform is a analog to digital converter, and you're back into zeros and ones. And the first I had heard about that was before I ran my very first quantum circuit. It was presented as we can map a terabit of data to only 40 qubits using this approach of essentially converting it into a wave and saving space. So they used that method, but they did it differently. They did it very differently using Huffman encoding. And at the time I'm talking to you now, I haven't fully reverse engineered that because they used a gate for ion Q that is not standard. It's not on IBM systems, which I'm more familiar with. So part of it is deciphering what does this proprietary, well, not proprietary, but this, I'll call it non-standard. I haven't seen an RBS gate presented anywhere else before, at least none that stick out in my mind. A non-standard gate and a different kind of encoding, but still claiming in the paper to achieve the same effect of compressing a lot of information into a much smaller space. And the best part of that paper is all the way at the end, and I'm trying to get QCware to spill their secrets. Otherwise, I'll eventually figure it out on my own anyway, but it'll make it a little bit easier. They make a subtle reference to dense amplitude encoding. So imagine instead of a terabit of data, and you're hearing me correctly, I'm saying terabit, compressed into 40 qubits, imagine a terabit compressed into only 20 qubits. It's a huge amount of savings. Moving on from Quantum MNIST, there are other things that we can do with quantum imaging. It's very much in its infancy, but it's amazing how much can already be done or how many algorithms are already developed, starting with quantum vector graphics. To save space, if you know anything about an image, you have all these pixels and all that information has to be stored. And with the vector graphics, you save space by saying, I have a pixel here, I have a pixel here, draw a line. I have a pixel here, draw a line, pixel, pixel, draw a line. And with a quantum image, the idea is that you have those pixels represented by qubits, and I have a qubit that represents a pixel here and a qubit that represents a pixel here. And when we measure, and we have to render the image classically, but when we measure, we can determine that these two qubits are entangled. Let's draw a line between the pixels that they represent. And these two qubits are entangled. And let's take those pixels, draw a line, and these two qubits are entangled, draw a line. And the idea is to encode graphics information within quantum entanglement itself, which I think is pretty cool. Then most of the image manipulation so far is still binary. Again, just 0 black or 1 white, but there are algorithms already in place for manipulating those images. Let's take a single pixel and represent it by 7 qubits. And that's the problem. We don't have many qubits, so 7 qubits per pixel is not very good today. But you can do this now. You've got 7 qubits. One is for color. You have 0 black or 1 white. You have 3 qubits representing the x-axis, which gives you 8 possible positions. 3 qubits representing the y-axis gives you 8 possible positions. And again, I don't know everyone's background. It's 2 to the exponent of 3, which is where the 8 comes from. And we have 64, an 8 by 8 grid, a 64 pixel image. And what you can already do now is, let's say you want to flip the image over the x-axis. You apply the Pauli X gate, also called the X, also called the not. I'll call it the X. I'll go in the middle. You apply an X to all of the Y qubits, and that flips over the x-axis. And you apply an X to all of the X qubits, and that flips the image over the y-axis. Or a swap operation, which is still one of the most basic operations. You swap the x0 and the y0, you swap the x1 and the y1, and so forth, and that flips the image over both axes. How practical is that? Not very, because images today are very detailed. But if you think back a couple of decades to how the images of today started, they weren't, well, compared to today, they're not impressive, but back then they were very impressive. I remember a friend of mine animating this tiny little ninja on his screen, and it was just a bunch of black pixels turning on and off. But that's how you start, and then it evolves from there. And also using a combination of the same 2 operations, just X and swap, you can rotate a simple binary image 90 degrees, 180 degrees, or 270 degrees. And a color transformation is simple also, because the color is represented by a single qubit. You just X that. If it's 0 black, it goes to 1 white, and if it's 1 white, it goes to 0 black. So if it sounds like I'm oversimplifying it, I'm actually really not. It's really that simple. When I saw the algorithm, I was amazed that's already been done with quantum imaging. Then let's see, are we at the good stuff? We're at the good stuff. Here's the interesting stuff. Everything else is boring. Some things that we can't practically do yet, but I'm pretty excited about, would be quantum watermarking. So I put an image on the internet, and you download it, you steal it, you use Photoshop to get rid of my watermark, and I say that's my image, and you say, well, I don't know how that works. I've never stolen an image before. But think about how a radio transmission works. You dial your radio, because that's how old I am. You dial your radio and you pick the frequency. And for AM radio, the sound is encoded in the amplitude modulation of that frequency. And for FM radio, the sound is encoded in the frequency modulation. So along those lines of a carrier wave, you have a carrier image, and you have a watermark image, and a quantum algorithm that combines the two into the image that you want to steal. And when you look at that image, you have absolutely no idea that it's watermarked. because of quantum mechanics, you can't possibly know it's even watermarked. But then when I say, hey, you stole my image, and you say, prove it, we can apply that quantum algorithm in reverse, and my watermark magically appears. So part of that is also using the quantum Fourier transform that I mentioned briefly. Again, you can think of that as a digital to analog converter, and then its inverse is the analog to digital converter. Just think of it from digital to analog and analog to digital. And also very exciting is encrypting images. Imagine we've got a satellite image, so there's information that we want to share, and obviously we don't want any enemy to get this image that we're looking at. And if you look at the textbook quantum teleportation experiment, and if you haven't heard of that, the name is far more exciting than it really is. If you're a Star Trek fan, it's nothing at all like that. So it's a little bit of a letdown, but you're teleporting information is what you're doing. And in this textbook algorithm, you have two people, Alice and Bob. And Alice gets information from Charlie, and she's not allowed to know what it is, which is thoroughly impractical, but that's the way a lot of quantum algorithms work. They work backwards. Here's something that works. Now let's figure out a way to apply it. Opposed to classical programming, I have a problem and I need to figure out a solution. It's a little bit backwards. Why would Alice not know what the message is? But between Alice and Bob, you have an eavesdropper named Eve who is trying to intercept it. And because of quantum mechanics, she cannot possibly figure out what the message is. But Alice and Bob, also because of quantum mechanics, will be alerted to the fact that there is an eavesdropper trying to intercept it, and then they can retransmit. So something else that's never mentioned with this algorithm is the fact that it's a good denial attack. It's usually focusing on the fact that Eve cannot possibly decipher it, but when she does that, Bob can't decipher it either. So it's a very good denial attack. And they normally send only 2 bits of information, and you can actually communicate quite a bit with 2 bits if you've got it prearranged. But imagine instead of just sending 2 bits, you just scale it up. Alice and Bob are sending enough bits to represent our satellite image. And again, if Eve were to intercept the whole thing, she cannot possibly figure out what the image is. It is completely secure, also still a good denial attack, but completely secure. And Alice and Bob can just retransmit until Bob has it. Then he can decode it on his end. Then I mentioned earlier quantum convolutional neural networks taking the feature and looking for it in an image. There is a more quantum version of that, which is mostly mathematical at this point, called local feature point extraction. And it's using a whole lot of math. And then after you do all these calculations, then using quantum operations, you then extract the features from the image. So that will probably end up being the better version once you work through all the math. And again, we can't actually practically do anything with that at this point. But if you can think of it along the lines of, let's say, a Hubble deep field image and how many pixels you have, some way to do that to achieve a quantum computational advantage. And finally, quantum movies are a thing. And as far as movies go, encoding audio makes sense because I already talked about how you can use waves, and we think of sound as waves. So that's not surprising, but the movie concept, imagine you have 1 second of a movie and you have 24 frames, 24 images, and each image takes up a lot of space, and 24 images take up even more space. And that's why there are algorithms like MPEG-4 that take these images and try to compress it as much as they possibly can. And the idea of doing it in a quantum way is mostly, well, two parts. One part is compression, that you have qubits, and instead of adding, in the case of a movie, you have the pixels of an image, then the pixels of the next, and the pixels and more pixels. You've got qubits, and you can just work with the qubits you have and save a considerable amount of space. But even better than that would be, as I just talked about with the satellite image, imagine a quantum CCTV. So I'm looking on my screen right now, I'm looking at quantum CCTV footage, and Eve tries to intercept it. Let's say I'm on some covert mission somewhere, and I've got some camera on my helmet somewhere, and I'm beaming the footage back to whoever's watching it wherever they are. And I sure don't want the enemy intercepting that. And if they do, they cannot possibly see the image I'm sending. Only back home can they see that. And like the satellite image, it's still a good denial attack. They're gonna they're going to get gibberish back home, but at least the enemy can't see what I'm looking at with my camera. And with that, uh, I lost track of my clock. I hope that was 45 minutes, and I will gladly take questions.
Okay, thank you, Brian. So if you have questions, just put your hands up and unmute yourself and ask.
Maybe I spoke too fast.
No, your pace was good. I see someone unmuted themselves.
Yeah, it is me, Captain Erdem. Can you guys hear me?
Yeah, so we can
Yes.
hear you. Go ahead.
Yeah. Sorry, I have a question, and I am interested with the subject just as an hobby, and I don't know if the question is the maybe I'm mixing the apple and banana together, but the week ago there was a presentation from Tesla company that they said the AI days, and they were talking about the all imaging, that they have their autopilot system with the 8 camera. They are collecting the all image, and they are trying to figure out which image is showing what. They told almost everything what you said in your explanation except quantum. Do you know, are they using the similar method to finding the or the clarifying the imaging or different system?
Well, all you could really do now would be a proof of concept. So I don't know if they're working on proof of concept for that, but everything would have to be a very small image that you're working with. And even, well, even the algorithm itself, any kind of method that you're doing now, you can't run it on real hardware. Everything has to be simulated. And because it's simulated, it means it's being run classically, and there are still limits to what you can figure out. So it's possible that I haven't heard of anything with Tesla, but it's possible they're working out the algorithms, but not actually doing anything with it at this point.
And they said because of the hardware is not compatible what they use, they are working on the new system they call dojo. And then I was thinking when you were explaining, maybe that's why the hardware they have to design for their way. But they gave some information, of course not the deeply, and then they didn't exactly say what method they use. But after your explanation, I am thinking maybe similar methods they come up with. Is it possible, you think?
Well, it's possible. There is, if you Well, if you go to archive.org, ARXIV, the repository of research, the problem is it's got so many names. You might find something, but because it's a company, they might not be writing papers. But it would be the best approach, or the alternative is variational algorithms, which again, I'm not a fan of, but the idea would be to do a lot of classical computation with a little bit of quantum computation, but you still can't do much with that right now. So out of the two approaches that they're likely to be doing, one would be a variational algorithm, which is very popular because it uses Python and Cheezkit or Circ or one of the other libraries, or kernel methods. I would say it's probably called kernel methods more often, but probably you would think that they'd be looking into that somewhat, but unfortunately I haven't read with Tesla what they're actually looking into.
Perfect. Thank you. Thank you very much.
Yep. I'm going to look into that next though. Tesla.
So there's a question from Paul, Drew Paulses. It's on the chat.
Yeah, I'll just speak up there. So it was great, and I really enjoyed the beginning of the presentation where you were referring how you implemented an Excel vice Python. I was just curious to see what that looks like, and I don't know if there was possibility of sharing, or what would that even look like in Excel?
I shared the end result in a Medium article. So the book that was mentioned earlier, I started off with a Medium article that kind of went step by step. This is what I did to get it to work. And then the book was more of a behind the scenes approach of what was I thinking as I was coming up with that. So I do have a Medium article that is pretty detailed, I think, and I probably still have the actual Excel file. So if we can work out some kind of system where I'll just give a link to the article and the file itself, I guess we can work out the technical of the best way to share that.
Yeah, that'd be great. Thank you very much.
Yeah, if you can send it to me, and I will send it to the group.
Okay, hopefully it'll make sense because it was kind of a worksheet for me. But I'll send it. I'm not guaranteeing it'll make sense, but then maybe that plus the article will say, okay, I can kind of see how we got to this point, maybe, hopefully.
And perhaps on the heckling, I thought it was very interesting when you shared the heckling. It's like, what do you think that the motivation was behind it? I was curious to see.
Well, if I was a YouTuber, I'd be trying to build up my channel and get likes and subscribes. And there was a video at one point walking through and trying to prove that it'll never achieve quantum computational advantage. But I don't remember if I mentioned it or not, the paper that suggested maybe the 50 qubit mark, if we compare 50 to 50 with one ancilla qubit, then maybe that'll be the quantum advantage. That was a team of MIT and Xanadu researchers. And even though I'm not a big fan of Xanadu, you can't argue with MIT. And one of the members of that team was Dr. Seth Lloyd, who is a pioneer of quantum computing. And so you have this paper with Dr. Seth Lloyd on it saying that we're suggesting this method could have quantum computational advantage. And then you have a YouTuber saying, my math shows it'll never achieve quantum advantage. I don't take it personally. I just say, you're arguing with this guy. You're arguing with this paper from Dr. Seth Lloyd. If you want your YouTube credentials, that's fine by you. And all I say is, well, like I'm doing now, I'll just throw a quantum pioneer's name out there and let someone argue with that. Doesn't hurt my feelings, but many other papers since then have also suggested not with that number, not with the number 50, but with their various mathematical proofs suggesting that there should be an advantage at some point. And then also, like I said, you can test it to an extent on a simulator, just load it up and at some point it breaks. Whereas if we had enough qubits, that really shouldn't happen.
Thank you. That's a very interesting answer. Thank you very much.
And then there's always the block feature. I use that a lot. Some arguments are just not worth getting into. If it's constructive, it was a great idea to use the MNIST data set, so I appreciate that. But then after, with the extra negativity, now just block, and I've got my answer over here. And ultimately what we need is enough qubits to test it out. For those of you who are familiar with O notation is the standard for how fast a quantum algorithm runs. And I'm not a big fan of that because, again, I'm an experimentalist. Let's click a button on the quantum and let's click a button on the classical and let's see what their actual run times are. Because you're comparing apples to oranges a lot of times. Let's say a quantum processor uses, or quantum algorithm uses less steps, but if we set how fast it is, we're talking about maybe millions of cycles per second, whereas classical processors maybe have more steps, but you're talking billions per second. So less steps, but millions versus billions, and it's apples to oranges. And quantum processors also have a lot of, you can test this actually. You take your quantum processor and take one qubit, put a Hadamard on it and measure it, and boom, you're done. How long does that take? And probably between 20 to 30 seconds. So that's why it'll never be useful to do math on a quantum computer, because the calculator is so fast. 2 + 2 equals, boom, it's instantaneous, the answer. But the shortest run time on an IBM system, last time I checked, the minimum is 20 to 30 seconds. But on the other hand, you can initialize all the qubits, load it up with 100 gates each, and you can see the maximum runtime. Maybe it's 30 to 40 seconds. So you know the minimum, you know the maximum experimentally, and then you ask the question of the classical algorithm, how long does it take to run? And is it faster or not? That's my version of O notation, the actual run times. And then you need a sufficiently difficult classical problem, which now we can't do quantumly. But if we had more qubits and we had fault tolerant qubits, and we have this classical problem that takes a few hours to run. And now let's compare that to Sycamore, Google's 53 qubit device, which had the runtime of 200 seconds to do its experiment. So 200 seconds, and how long does this classical problem take? Okay, it's faster. That's just my personal cheat. Any other questions?
Let's wait a few more seconds and see if anybody jumps in.
I don't know how strictly you keep to your timeline. I'm free for more questions, or you can share my email address. You can share my LinkedIn, Twitter, any of that stuff.
Sure, I'll definitely do that. So yeah, I think that's all the questions for today. So Brian, thank you very much for sharing your experience and knowledge in this field, especially from my side. As you know, do my work in variational algorithms, so I don't look at the imaging and the video and audio side of things. So thanks for broadening the perspective on that the spectrum. And yeah, so I will share your email and LinkedIn with everybody in the team, and they can build further connection with you as we go on. So thank you very much, Brian. Thanks for taking your time.
Thank you very much. All of you, thank you very much.
And
Thank you.
Phil, do you have any last message?
Nope.